Okay, you're live.
Okay, welcome to the Spartan series for our last talk. I wanted to give a talk on kind of how we designed AOS 971's middleware, and then try to tie that back into how you can take some of the lessons that we have learned through this process back to your own software a little bit. Like, what does it take to build more complicated robots? So basic outline, let's start with where AOS came from, kind of what we've learned, and then start talking about the design goals and constraints, and then start working through what we've built, and then get some examples, and then show some places we can take this. So what is AOS? AOS is a middleware layer. Middleware is best defined as kind of the glue code. It's the code that helps connect your systems together and helps you build your software. So why should you care? You can start very simple in FRC and start writing simple software and build plenty competitive robots. But as you start to build more complicated software, especially as you try and take this towards industry and try and build things like autonomous cars, we need good frameworks and good tools to help us manage all that complexity. And those tools should also give us the ability to debug and do dependency injection and really help us test out our system. So where did we start? We started AOS in about 2011. The initial API and design we found was rather limiting. So we built a pub subsystem. It's a publisher subscriber. So it's based on sending messages around between various different systems. We had a custom compiler that generated some C structures. We could only wait for one message at a time. And then we had a lot of trouble figuring out how to simulate, how to replay data. So say we recorded something during a match and we wanted to see how our system would behave once we fixed the bug, or how to kind of test larger parts of the system. And then the other limiting part that was very frustrating was every time we added a field or added a sensor, we could no longer read any of our old data. So we had trouble building up this historical data set to help us grow. So around fall of last year, we decided it was time to rewrite it. So what were our design goals? So we want to support running code on the robot, writing test cases, building simulations, and taking recorded data from the robot and running that through our system and seeing how it would perform. And we don't want to have to modify the code. So basic idea is you have your code you wrote, you put it on the robot, it does its thing. You could also take a log file and kind of feed it the same way and get insights from that and see how it would perform, or build a little simulation. So you can do a lot with a little F equals MA simulation and see how your robot would respond and kind of be able to tie those all together. Our other goal was FRC. Everything runs at about 200 Hertz. That's the fastest you can command your motors over PWM. So we want to be able to use this system at that speed. We can't have it pause for multiple milliseconds because that would cause us to skip a cycle. One of our other design goals was to have all of the interactions that our developers have with the system be single-threaded. Developers have a hard time writing multi-threaded code, so if it's possible to keep everything single-threaded and keep the interactions simpler, then that helps us a lot. So here's where we get to one of the more complicated concepts. So loosely coupled. Basic idea is when we talked about running on the robot or running with logs, we need to replace parts of our system really easily and be able to try new combinations, especially with testing. So loose coupling means we want to be able to swap parts of our system out very easily to try different cases. Fast, the RoboRio is fast. It's got a lot of computation, but you can quickly use it all up. So we don't want to waste a bunch of CPU on that. Reflection available. So we want to be able to write efficient tools, but also write some generic tools. So what if we could go look at any message or be able to kind of debug our system with tools that we built. Everything logged. There's nothing worse than coming out of a match where something broke and everyone looks at each other and says, I don't know what went wrong. So we want to have everything possible logged so we will never find ourselves in that case. So we'll have all our inputs logged, all our outputs, all our decisions. We want to be able to figure out what went wrong in that match. And then building off of our previous iteration, we learned that building our own message formats was probably a bad idea. So our goal was to be less custom. So that's to use off-the-shelf messaging formats and software wherever's reasonable. Okay, so let's break this down per kind of subsystem. So what do we care about on the robot? Deterministic. So the RoboRio is pretty good at being deterministic and running our code reliably. So we want to not make that any worse. Bounded latency. So this comes back to we want to meet our 5 millisecond control loop cycle. So we don't want our any of our system to accidentally take too long and cause us to skip a cycle. Run at normal speed. This is almost a little humorous, but we don't want our code to just spin there and burn a CPU. We want 5 milliseconds to be 5 milliseconds. Robust. So if something goes wrong, say we have a bug in our superstructure or our debugging or our diagnostic code or the logger or something, we don't want that to take down the rest of our system or even autonomous mode. We want the rest of our robot to continue operating and that subsystem that broke to recover. So this really pushes us towards a multi-process solution where each one of these processes can crash and the rest of the system recover. Fault tolerance is a really big deal as you start to build more complicated systems. And then fast enough, as we are starting to grow on 971 and grow our software further, we are looking at using cameras and images more. And we need to make sure that this will work for those type of systems. Okay. So what do we care about when we're building a simulation? We want it to be completely deterministic. If you do something once, we want to do it identically the next time. So this helps you find and reproduce bugs reliably and repeatably and write good tests. So faster in real life. Don't want to wait 100 seconds to run a 100-second simulation if we don't have to. This kind of goes back to deterministic. It's easier to have it do the same if you're not relying on your operating system. And then we don't want to change code. When we build our simulation, we want the same code that's running on the robot to run in the simulator. Log replay. So this is our other case, our third case. So we have some data we recorded from the robot, and we want to kind of feed it back through our system and see how it would respond. So deterministic again, when we feed it through twice, we want it to get the exact same results. Faster than real life. So this is like simulation. We don't want to have to wait. We then want to take data and times. So not everything's perfect from our real system and feed it back through our code and see how it would have responded. And then this is a lesson from our previous system as we evolve our data. So as you add new sensors or change internal information, we want to still be able to reuse that data. So that data you collected at your first regional, that's super valuable, but then you added that new sensor, we still want to be able to use that to continue development. And then again, same interface as the robot. We really want to be able to reuse the code in all these various environments. Okay, so what do we need to do this? So the first thing we're going to do is we're going to pick a publisher subscriber mechanism. So use message passing to let us decouple our system. And we want it to be N to N. That should probably be M to N. But any number of publishers and any number of subscribers within reason. And then so this means we need to build a mechanism to transfer messages and to be able to communicate between our various subsystems. Then the other thing is we talked about having time operate differently on our robot and in our simulation. So we need a way to abstract out time and encapsulate that. Okay, so here's where we're at. So we got a publisher, we got a pub subsystem. So we got, say, 2 publishers here, and then that puts messages in a queue. And then we go pull those messages out of the queue, and the subscribers can read them. And then we can have multiple queues for different message types. Okay, so what next? So we got to figure out what our message format looks like. So here's some various options that we evaluated. Kind of the big leading one is protocol buffers. So those are very wide. They're from Google. There's a lot of support for them for a lot of languages and a lot of options. As the schema evolves, as we add and subtract fields, protocol buffers support that very nicely. That's one of their defining characteristics. They have reflections, so you can go and ask them what fields they have and what data is inside them. And then if you want, you can go print those binary messages back out as text, and people can then look at them. So it's got a way for people to interact. So the downside is you build this message up, and then you call the serialize function, which then copies it all. And then you call the deserialize function on the other side, which then copies it again. And so we've added a bunch of copies, and that slows them down. which goes against our limited resources. So another option is cap and proto. So this is a 0 copy message format. The basic idea is instead of doing serialization and deserialization, you just directly build the message. And then whenever you want to read it, you can just directly read it. So we avoid those 2 copies. So that makes it fast, a lot faster and a lot more suitable for this type of stuff. So schema evolution, so it also supports adding fields. It's a lot faster. It has a reflection and can support reading data or printing things out in an ASCII version. So that's all good. The downside, which was kind of tough on us, was it does not provide a good mechanism for telling which data was available when we logged the message and which wasn't. So if you go add a new field, it doesn't tell you that that field was not present when you logged your data. So this brings us to the format that we ended up selecting, flop buffers. So they're very similar to cap and proto. There's 0 copies, so we can make them very efficient. They support changing our schema. They're fast. They support printing things out, in this case in JSON. So that lets us kind of visualize and see what's going on. They support reflection, and then they have a mechanism that lets us see if something was populated at the time of serialization or not. So this lets us tell if we have data from before or after we added our new sensor. The downside is the API is a little bit more wordy and cumbersome, a little harder to work with. But we thought that was not enough of a reason to push us to do something else. Okay, so where are we at? So we got a publisher, and it's publishing flop buffers into the queue. Those flop buffers are then being read back out to the various subscribers. Cool. Okay, so let's start talking about time. So how do we abstract time out? So we want to introduce a concept of an event loop. The basic idea is you have a list of various events, so things that need to happen, and you sort them. So you have what will happen first and what will happen later. And then you have a loop that just keeps processing events, processes the first one first, and then goes and looks and see if there's any more, and then processes the next one and repeats. So this lets you provide kind of an interface to abstract out the execution. So then like so here we have a timer. So you could schedule something to happen in the future, and then you could give it a function to call when that timer happens. And so it would give you ability to get your code called. And the same here with a flop buffer. Whenever we get a message, we could then have a callback called with that new message, so we could process it in the event loop. Okay, so how would this look on our robot? So we have multiple event loops. We have one on the receiver side. It's got some various timers, and it's receiving flop buffers, and it processes them as the data is available. And then on the publisher side, so this would maybe be like in WPI lab code, we have various timers waiting, and then those, whenever those trigger, our event loop calls them, and then we can send a message, for example. So cool. And then we can have these 2 event loops running in different processes to give us that abstraction and isolation that we want. Okay, so what's simulation look like? Well, we can reuse a lot of these same concepts. So we have our event list for our publisher and for our subscriber, and we have our queue. And then instead of having 2 event loops running at the same time, we just pick the oldest event out of any of our event lists, and we just process it in our loop, and we repeat that. So this lets us actually intermix all these events and schedule them together. So we can preserve the same interface for our code and get different execution environments. So log replay, we can reuse a lot of these concepts as well. So we just have a log reader, which takes messages from a file, and it places them in the queue at the correct times. So this is kind of cool, because what we're able to do here is we could actually replay logs on the robot, or we could replay logs in simulation. And that gives us some pretty powerful things we can do. Okay, so let's look at an example. So this is our 2020 robot software design. You will probably notice this looks very similar to 2019 and probably 2018. So it's been a pattern that we've been using for a couple of years. So we have this process called WPI Live Interface, and its job is to read the sensors. So it reads all of our encoders and reads the joysticks, and it publishes out a message. So then say we have drivetrain or wheel speed encoders. It'll read those. It can then process them, figure out how to do the controls, and then it sends back a message saying, here's the power to apply to our left motor. Here's the power to apply to our right motor. Same for the superstructure. We get the sensors for like In 2019, we had our elevator and our wrist. So we got the 2 sensors for those. And then we'd process those, and then we'd send back the commands to make them move. Okay, and so then joystick reader. So on purpose, we're trying to keep WPI-Lib interface simple. So it's just publishing raw joystick readings. We don't want our drivetrain and superstructure to look at those directly. So joystick reader goes and takes all the buttons and figures out what to tell our drivetrain and superstructure to do. So it'll tell our superstructure to go to a position or spin the flywheel up to a speed based on whatever the user pressed, or tell our drivetrain to drive at a speed or a radius. And then it also triggers autonomous. So, and then when autonomous runs, it uses the same interface as joystick reader and spits out goals and tells the superstructure where to go and the drivetrain where to go. And then down here at the bottom, there we go. Down here at the bottom, we have the logger. So this just listens to all the messages and writes them down. So cool. So let's talk about that logger some more. So we want to capture what actually happened. So this means we want to know what messages were actually sent, not what we thought should be sent, and also exactly what times they were sent. A subtlety here, we actually want to implement this on our event loop abstraction, because this will let us develop log files for simulations if we want, and then also build log files for things that ran on the robot. And we don't necessarily have to do it this way, but if we can reuse some of these concepts, then we'll enable use cases that we never would have expected before. So another key thing to think about with a logger is when we write things to disk, it's not real time and it's never going to be. If you think about your old steady state hard drives, you had a disk spinning around and a head moving, and sometimes the head just wouldn't get there in time. So or you'd have some vibration and the head wouldn't be in the right spot. And so the disk would just wait, and you just never know how long that's going to take. So we want to design our logger so that we take that into account. So this comes to our next point. We never want the logger to be able to block our real-time system. So as it's going and reading these messages, we want it to never block our system. We don't want it to affect it. There's also kind of a contrary point here. So we want the logger to not miss data, because if we're missing data, that's really hard to debug what happened. So those are kind of in conflict. If we can't delay our system and we don't know how long it will take to log, but we don't want to miss any data, we can't really succeed there. So we end up with a compromise. We say, okay, we'll give the logger, say 5 seconds or 2 seconds to write everything to disk. If it can't do that in time, then we will write down that we couldn't write something to disk and capture that. So we end up with a new requirement from here, and that is that we want to save the last, X seconds, in this case 2, in the queue. We would have to copy that data anyways, to copy it out of the queue to save it for the logger. And so we'd be using the memory anyways, so we might as well have the queue hold that memory. Another requirement we want is we want this log file to be self-describing. So if I hand somebody a log, I shouldn't have to tell them exactly what's in it. They should be able to read that log and look at it, and then come back and be able to analyze the data. And then here's another real challenge here if we're not careful. So we need to be able to tell the logger what to log. So this is in larger systems, this can be called the discovery service. It's essentially answering the question of what messages are available. And then it's kind of a minor design point, but where possible, let's not make the robot have to do more work. Let's make the reader have to do more work. So this is kind of implementation detail. Okay, so where are we at? So we have our publisher, it's publishing flop buffers. We're storing the last couple seconds of those in a queue, and then our subscribers can then read those. And we have multiple of these queues. Okay, so we talked about how do we find these channels? Well, the easiest answer is we just write them down in a file. So here in that file, we can actually make a flop buffer because we can write it out as JSON. So here's an example. So we have ping and pong. So we have a channel with a name of foo, and then we're going to put a ping message in there. And then before we talked about wanting to save the last X seconds. Well, to do that, we need to know how fast the message is coming out. So this channel list gives us a nice place to put that type of metadata. So here we have our frequency field. So this ping message is going to come out at 200 hertz. So we need to allocate enough messages in that queue to store 200 hertz of it. So we can do that with ping and pong. And then a cool side note here is this is actually a place we can put the schema. So the schema is actually a flat buffer describing what all the fields are in the flat buffer. It's kind of flat buffer inception here. And that means that once we've read this configuration, then we actually know how to interpret that data as well, which lets us build some pretty cool tools. Okay, so let's go into some details about what this queue looks like. So I'm almost a little hesitant to present on what the queue implementation is, because there's a lot of really tricky details and it's almost distracting. But I think it's worth talking about it to kind of explain what some of the trade-offs we can make down here are and how they impact our system further up. So in order to get the zero copy and the speed we want, so we can move large amounts of data, we need to use shared memory. So this is a piece of memory that we can share between two various processes and put data in. So we said we didn't want the logger to be able to block the rest of our system. So no matter how hard you try on a real-time system, it is very hard to make that perfectly true without actually going to a lockless system. So the idea is rather than putting mutexes, so only one person can read or write at a time, we have to write enough information down and define enough strategies that two people can simultaneously read or write. Robust to crashes. So we said before that we want parts of our system to go down and us to be able to recover. That only works if the queue does not get corrupted. Because if this got corrupted and then we could no longer read and write to it, that would break that concept. So we have to do some bookkeeping to help make sure that nothing can corrupt this. If you're interested in a lot of the nitty-gritty details, we have some design docs and some pretty good comments in the code. So let's go. So we want to write it. We want to publish some data. What's the high-level picture? So we have a list of messages pre-allocated based on the size and the number of writers. So we go populate one of these messages, and then here we have a queue of pointers, a circular buffer. So we go write it. We say, okay, we're going to write message number 1000 next. So we figure out which slot it goes in, and then we move the pointer, and we can move that pointer atomically. So that gives us that's a lockless operation. And then if we want to go read, we can say, okay, we want to read message number 999. So I can go look up, okay, here's which slot it should be. Now I can go look, see if the message points to what I think it should, and then read it. How do we read this locklessly? The idea is you have a number at the top. It's that message number, kind of which one you're supposed to be reading. So you go read that number, and then you execute a barrier. So this is to guarantee that read has finished before you do anything else. And then you go read all your data, and then you put another barrier in, and then you go read the number again. And if the number has changed while you're reading the data, that means someone published a new message on top of you, and you have to throw it out and try again. So the corollary to this is if someone is writing a message, they have to modify the message number before they modify the data. Because you'd imagine if the reader was going along and they read the message number, read the data, read the message number, and the message number is matched, but someone had modified the data while they were reading, that would fail. So here, if we modify the message number first, if we're reading data and somebody tries to read out or write over us, they'll change that message number first, so we'll know that the data has been corrupted when we go read it and it's different. Okay, so we have a lockless queue. So some other notes about it. For small pieces of data, so say you have an 8-byte CAN message or a couple bytes of sensor data that's really small, it can actually be sometimes faster to copy that data. Processor caches are pretty crazy rather than leaving it in shared memory, leaving it in that message. There's a fancier version that we're not going to go into where we can actually guarantee that the message won't get changed out from under us. This is called pinning for us. So it means the message will never get overwritten while we've got a reference to it. And that lets us implement true zero copy. And then there's a huge number of details about how to deal with recovery and all that. We got a design doc and a bunch of test cases. The thing to point out here is we can make choices, and we have made choices down here that have a large impact on higher level system design. So say we decided to use a web server to move our data. Well, we'd have to run it over potentially TCP. We'd have to run it through that. We'd have to send it to the server, and the server would send it to the other clients. So that's going to have copies, and that's going to, there will be locks associated with that. Yeah, so we get a lot of choice here. Sorry, let me rephrase that. The choices we make here can have a large impact on what we're doing higher up in our interface, and what guarantees we can pass on to our user and what we can't. Okay, so let's present the interface that we have. So we got an event loop. It has the ability to make a sender. So you can pass in the type, and then you can pass in the name. So I can publish a ping message on /foo. And then we got a watcher. So this also takes, oh, and then it returns a sender object that you can manipulate to send data. And then we have a watcher. So given the same type and a name, it will then, and a callback, it will schedule it so that whenever a message is received, the callback's called. So now we have a way to receive messages and process them in our event loop framework. And then a fetcher is kind of a polling interface. So we provided a type and a name, and it gives us this object that lets us say, give me the latest one, the latest message on this channel. And then our last kind of big interface is around time. So we can schedule a timer. So we give it a callback, and it makes us a timer. And then that timer gives us a method that lets us set when it should expire and call the callback, and then the repeat period. So say we wanted to start in 1 second, and then every 5 milliseconds call our callback. So we'd pass in now plus 1 second for the base, and then 5 milliseconds for the repeat. And then that would schedule this timer to get called periodically. And then the last part there is that's kind of waiting for time. The corollary to that is reading time. So we need a method to read our clock here. So that's our monotonic now function reads the current clock. Okay, so let's go into fetchers a little bit. So a very common pattern is you register a callback for the goal. So you just save it because you can't do anything. And then whenever your new sensor reading comes in or your periodic timer, you run your PID loop, for example, on that position and with that goal. So this sounds great, except we have to copy the goal, and that's a little bit expensive. And then also it turns out it's pretty expensive to wake up and save that. So every time we receive a goal, it'll take us, say it'll take us 50 to 100 microseconds to wake up and write that data down and go back to sleep. And that's work that we really didn't need to do. So the optimization we can do with a fetcher is down here. So every time we get a position, we just go ask the goal fetcher, just give me the latest goal. I don't care how many have happened since then. I just want the latest. And then we can run our PID loop on that position with that goal. So we avoided a wake up. On some systems, I've seen this reduce CPU utilization by like 50% or more. So it can be a pretty big deal. Okay, so let's go through an example. Let's run ping and pong through this and see what it would look like. So we have a ping process. It publishes a ping message. Pong receives it and replies back with pong. And then we can measure the round trip time because we'll put timestamps in all the places. So what's our ping message look like? We've got a ping, we put the value in, and then we have the timestamp. We write that down. And then pong, it's got the same value. So this is the number that we're sending back. And then it has the time that ping was, the time from ping. So we can track that all the way through. Okay, so then what's our ping process or our ping module look like? So it takes an event loop, which has set everything up. And then we have some methods. So we have a send ping, which will send the ping message out. And then we have a handle pong to receive it. And then here's our event loop handle just for reference. And then here's a timer. So we can schedule the ping to be sent. And then here's the sender to send it. Okay, so what's setup look like in ping? Well, save the event loop. Now here's where we make a sender. So this gives us the ability to send that ping message. And then here we can go make a timer. And that timer will call ping whenever it expires. So that lets us periodically send a ping out. And then here we make a watcher. So we're registering a function to get called when the Pong message is received. And then here's a new concept. So on run is a function that calls right before our event loop starts up. So this lets us like grab the current time and schedule things in the future, because you never know how long between when something's set up and when our system starts executing. So we set that up. So we'll start now, and then every 10 milliseconds, we'll expire the timer, which will send the ping out. And then here, so on our event loop, we can then set the priority. So we can interact with the scheduler. Okay, so what's send ping look like? Well, we got to increment the counter. Then we go make a flat buffer builder here. So we tell the sender allocate a message in shared memory for us. And we start filling it out. So we make a ping message, set the value, set the time, and then send it. Okay. So now let's look in what's Pong do. Okay, this should start to look a little familiar. So we got a constructor, which takes the event loop. And then we have a reply function. So it takes, receives the ping and sends a Pong out. And then here we have a sender for Pong. Okay, so this, again, this should start to look familiar. So here is where we're making our sender again for Pong. We save it, and then we register a callback. So whenever we get a ping message, we send Pong back. And then here we're setting it so we also want this to run as a real-time process. We do this through the event loop because in simulation, it doesn't make sense to be real-time. So we want to be able to allow different behaviors in those two environments. Okay, so what's sending a Pong message look like? Well, we make another builder again with the sender, make a message builder, and then we take the value out of ping and we drop it in. We take the send time out of the ping message, drop that in, and send it back. Okay, so let's look at where we receive it back in ping. Okay, so a callback for the Pong message. We read the timeout. We take the current time, we subtract them, and that tells us how long it took. Cool, okay. So let's start it up. So here we're going to initialize AOS, read that configuration we talked about where we can discover channels. And then here we build a shared memory event loop. So this is our real-time event loop. We build it off that configuration. And then we register everything with ping, so set that up. And then we tell our event loop to just run forever. And so then it sits there sending ping messages and receiving Pongs. Okay, and then Pong looks very similar, so I'm not going to show it. So how would we test this? So here's a super simple test. So this makes a simulated event loop factory. So rather than a real-time one, this is our simulated one. The factory is the thing that holds all the event loops that need to get scheduled together. So then we can make one for ping and one for Pong. So this lets us, well, essentially have two event loops, one for ping and Pong, where we can schedule all the events. So then we set up ping on the ping loop, Pong on the Pong loop, and then we can run our world for 10 seconds. So pretty cool. We're able to here take ping and Pong and let them operate. But let's take it a little further. Let's actually test something. So and what we could do instead is we could add another event loop for testing, have it subscribe to ping messages, and then just make sure the ping value increments and it matches what we expect. So it should start at 1 and work its way up. And then here on Pong, we're going to go confirm that the counter in Pong will just every time it'll increment. Okay, and then oh, that's covering the last little text. There we go. So then we can run that for 10 seconds and then confirm that there's 1,001 pings that were sent. So pretty cool. We're able to take something and run it both in the real world, and then also run it in a simulation and confirm the properties about it without modifying the code. Okay, so we talked about the typed interface. We'll briefly introduce the reflection interface here. It should be very similar, just won't have very many types. So in our configuration, we have a list of channels. So you can pull out a channel or find a channel. And then if you want to make a sender, you pass that channel in and it gives you something that'll let you just send chunks of memory. Those have to be well-formed flat buffers, but you can send those. And then you can also register a watcher. So given that channel and given a callback, it'll call you whenever a block of data is received. And then here's the same for a fetcher. So given a channel, we can get a fetcher to return that raw message. And then here's kind of an example down here at the bottom where we can write a function called flat buffer to JSON, which given the schema that we said we logged in the channel and the data, we can actually generate JSON. So that's pretty cool. We can go and register various callbacks and interact with our system completely reflection-based and start to manipulate it and work with it. Okay, what else can we do? Oh, I should add, this is the interface here through fetchers and timers and everything that we use for building the logger because we don't want to bake types into it. So what else can we do? If we've done our homework right, we should be able to extend this concept pretty nicely and do more things with it. So we have a message list in our config. We have a schema that we logged in that configuration, and we have a reflection API. So we can take that flat buffer to JSON function and then write a little command line tool that, given the channel and type, it just prints out the message values live. So cool. This actually gives us a tool that we can go live, inspect our robot and see how it's performing and see what it's doing and thinking. We can do the same thing for a log file. So if we logged those data, that message, or those messages, we have that message list in the top of the log file along with the schema. We have all the data. We can replay that, register a callback, the very same callback as before, and print out all the data from our log file. So that's pretty cool. What else can we do? So we want to understand how real-time our system is, how much latency there is, and how long things are taking to process. So let's talk about what latency means for a watcher. So we have a point in time, say in our first process where we publish the message, so that's where the event's triggered. Some amount of time later, the operating system starts executing our second process. And at that point in time, a little bit later, it starts our callback. And then sometime later, after we're done running our drivetrain controls or joysticks or something, our callback finishes, and then we're done. And eventually we go to sleep soon after. So we can track the two latencies here. So the latency between when the event was triggered and when the callback was started. So that's kind of how long it took to wake up and start processing. And then we can also track how long it took to process that event. So we can write down min, max, standard deviation, and go log this and publish this out. So the same concept applies for timers, these same things. So instead of a publish time, like when the message was published, it's really when the timer should have fired. And then here we have when the callback actually started. So, we're supposed to fire at t=0, but, half a millisecond later, we actually got started. And then it took a little bit of time to process it. So we can track the same statistics here. And then we can also track statistics on fetchers. So when was the message published? And then how much later did we actually pull it out and process it? And then rather than create a new mechanism to expose this data, we just put it in a message and publish it. So this message gets automatically published on /AOS with a type aos.timing.report. And this is automatically available for any event loop, both simulation and real time. So that's pretty cool. That lets us kind of monitor system performance. What else can we do? We can build a parameter server. The basic idea is you have calibration constants. We need to know what 0 is for our potentiometer. We need to know potentially what set points are and all these things. We can just put them in a message, publish it out on startup, potentially out when republish when it changes. So what's this get us? Well, that message is now logged because our logger knows how to log it, how to log messages. And then it's introspectable. So we can actually run AOS dump on it. We can run logcat on it. We could do all sorts of things to kind of get our hands on it and see what that message looks like. So that's pretty cool. We were able to do something new without really creating a new concept. So that's a good sign for us having a good set of concepts. So what else can we do? Well, turns out there's TypeScript support and JavaScript support for flat buffers. So why not make a web server? We can have various web pages, then go and grab data from a robot. You can do it via WebSocket to stream. We've been playing around with WebRTC to transfer flat buffers, or you could just make a little server that responds to GET requests. And you get a channel and a type, and it just gives you the JSON back. And then you can go put it in a web page. So this gives us the ability to build some pretty cool generic graphics and start to really understand what our robot's doing and thinking. This is a place where we're actively working because you're never done visualizing, and the better you can visualize what's going on in your system, generally the faster and easier it is to debug it. Okay, so what else can we do? So one of our challenges with picking shared memory is when we pick shared memory, messages don't magically go across networks. So say we add a Raspberry Pi to do some vision or some other coprocessor, that processor will not be able to get access to the shared memory on the RoboRio. So we have to figure out how to move our data. Well, why not teach the pub sub system? So publishers, subscribers, there's nothing saying they have to be on the same computer. So we could just magically have the data get moved. So we want to start logging information about this. So we don't want to move everything because if you have a bunch of data, it'll actually consume a bunch of CPU to move it. And if nobody's looking at it, you just don't care. Time to live. If I have a position message or something that I want to send over, or a camera message or something, at some point it's no longer interesting. It may be 1/10 of a second or 100th of a second or a second or 10 seconds, but at some point in time that becomes no longer interesting. We want to drop it on the floor. And then we want to log this configuration because we want to be able to figure out what happened in the past when we go get a log file and see why something happened or didn't happen. So to support this, we need to introduce the concept of visibility. So the idea that a message is published on one node and whether or not it is forwarded to another node. And then we want to also enforce this because we don't want to subscribe to a position message or something in the drivetrain on a Raspberry Pi or our vision processor and have it not be available. And so we just silently don't get the data. We want to know quickly and make that clear. We make some simplifying assumptions here that only one node publishes a message at a time because we can synchronize that in shared memory and networks are hard, so we don't want to do that. But in practice, we've not found that to be limiting. So another key thing here is we want to log what actually happened. We don't want to log what we thought happened. So if somebody sends something, it may not get to the other side. We need to know that. And then we want to make simulation have the same constraints. So we need to introduce this visibility concept into our simulation as well. Okay, so multi-node reordering. So basic idea, we're talking about, things might not make it. Well, they can also get swapped in time. So we have our message that gets sent at time 1. It shows up sometime later. Message 2 never makes it. And then message 3, well, it gets delayed a while and gets there actually after message 4 was sent. So we want to log the timestamps when all these messages were actually received, as well as if they were received. So we can actually replay this. Because what if we found a bug? Say we were trying to log some data, or say we went through a match and something didn't work and we have a log. And the problem was that this message 2 that told us to score, never got through. We want to make sure that we log the fact that never got through so we can reproduce that environment and simulate it. Okay, so to kind of replay things in order, we really want to see when we replay and when we simulate that causes should happen before effects. It sounds kind of obvious, but if we send a position message to make something go somewhere, we want to see that position message or see that goal message before we see that thing move or the command come out. So to do that, we need to be able to order messages across nodes well enough to guarantee causality. This only needs to be as good as the network latency, because if you send a message from A to B and it takes a millisecond to get there, if you're half a millisecond off in time, you can't have actually propagated that information across your network by then. So your order will be correct. Your time might not be perfect, but you'll still maintain your order. So this essentially boils down to the problem that we need to estimate the time on node A as a function of node B, the time on node B, and that'll be some offset as a function of time B plus the time on time B. And then as we go from one RoboRio and 1 Pi to this last year, we were looking at 5 Pis and a RoboRio. We really just got to use matrices here rather than single values. So the naive answer solution would be to just use NTP. the network time protocol. So that would let us just synchronize our clocks, but NTP has some challenges. Time will jump. So like if you have leap seconds, you'll get time jumps. Also, as your laptop connects and time synchronizes, time will jump. Or if you get a disconnect and reconnect, you can have time jump. And jumps could break this causality. So right across that time jump, not everybody will jump at the same time, and we'll have a problem. So startup's also really bad for this. And then what can we do that NTP can't? Well, we can look into the future. We have a log file with all the data. We can just grab it and sort it and then replay it and figure this all out. So here's a fun plot from some pies we were playing around with. So this is, you take a message on node A, you send it to node B, and you take the timestamp on A and B and you subtract them. And then you do the same for messages going the other way. So from B to A, you take the time on A, subtract the time on B, so they have the same sign, and then you plot them. And so this little gap down here, this is actually the network delay. So you can see how these cluster really nicely. And so our time estimate just needs to run down the middle of those two fuzzy lines. So here you can see over the course of, what is it in this log file? 50 seconds or so, we're seeing about 5 milliseconds of drift. So not bad. Cool. Okay, we have a question. Have you guys looked at supporting other languages, especially Rust? We have not looked at it. We did make some conscious choices in our message format. So flat buffers support a bunch of languages. I believe Rust is on that list. It was actually super nice for us that TypeScript and JavaScript were, so we could interact with flat buffers in web pages. We have not gone and ported any of the lower libraries down because we do not have a use case for them ourselves. But if other people are interested, we'd love to collaborate and kind of talk through. The concepts in PubSub are not language specific, and the data formats are not either. So it should be it should be possible to mix languages there. It'll be a little harder to deal with simulation because you'd have to run 2 languages at once. But that's doable. There's ways to make that work. So let's show a multi-node example here. So we're going to take our previous drivetrain from 2020 with our superstructure, and then our drivetrain is trying to estimate where it is on the field. So it's trying to localize. And so we can take each one of our pies over here with a camera running feature matching. So this is looking for objects on the field that we know of, and then it publishes those out and then records them. We record them here. And then also on each of these cameras, we're publishing out the images. So that lets us then record with our logger those images and rerun the processing later. So then we have our new message bridge client and server, which go and shuffle the messages around on the network. And then to avoid moving all this data all the time to the Rio and overwhelming it, we have a logger here. So logger logs everything individually. So cool. Okay. So far we've been in our simulation world. So we should talk about what interfacing with hardware looks like. Hardware is where everything gets tricky. So basic concept here is if you make a mistake in interacting with your hardware, you can't fix it later. So if I accidentally multiply something by 0, well, I kind of destroyed that information, or I round it. I destroyed it. I can't fix that. So we want to log and publish from our hardware layer messages containing the data from the hardware, but we want them to be as simple, as unprocessed as is reasonable. That lets us then not introduce bugs by accident. And then a lot of hardware likes to use something called select and epoll. So we need to support that. So what's select and epoll? It's a tool that it's a syscall on Linux and on Unix's selectives that lets you wait until a file descriptor becomes readable and or writable. So what are some interesting file descriptors? Well, we can open sockets. So we can have a socket which becomes readable when we get a UDP packet. So someone sends a UDP packet, now we can wake up our event loop. So we can also do that for TCP, so build a little TCP server the same way that'll interface, or it turns out CAN is actually a socket. So we could get data on the CAN bus. This is not the RoboRio CAN bus. This would be a socket CAN bus on another processor or larger systems. So what are some other fun file descriptors we can play with? Well, it turns out there's one called a timer FD. So it's a file descriptor that becomes readable when a timer expires. So now we have actually a way to make ePOL wake up when time happens, when time is expired. And then a signal FD. So whenever a signal fires, we can make a file descriptor become readable. So this lets us go and have our publisher poke our subscriber and say, new data, go check, go look in the queue. And then another fun one, V4L2, the video for Linux 2 subsystem, will give you a file descriptor that becomes readable when a new image is available. So we can actually then open our camera and get a file descriptor and be notified when there's a new image to process. So then how does this fit into our system? Well, now we're digging a little bit deeper into how our robot loop works. So we have a list of various events that can happen. So we have, for timers, we'll have a timer FD. For all the messages, we'll have a signal FD, and potentially sockets for any other interfaces. And then from there, ePOL then sits at the bottom and it goes to sleep and waits until there's something to do. So a timer or a signal or an image or something, and then it wakes up, calls the callback, and then goes back to sleep. And we just repeat this process. So cool. So, so for interfacing with hardware, if we can get it to fit in ePOL, our real-time event loop that we're running on the robot supports ePOL, so we can just plug it in. What are some other options? Well, if you think about WPI-lib, there's a function to read the current encoder reading. Well, we could just wake up at, say, 200 hertz or 100 hertz or whatever frequency we want and just poll the hardware. Just call the function and publish the message. This is pretty much how we read the hardware on 971. We just wake up periodically, read all the sensors, build messages, publish them, and go back to sleep and wait. So the last case, if one of those strategies doesn't fit you, you could just skip the event loop and call send. So imagine you're trying to write like a UI with Qt or GTK or some complicated framework, and it really doesn't want to let you run AOS's event loop. You can just, say someone clicks a button in the UI, we could just call send and just publish the message and just go isolate that away from the rest of the system. Cool. Okay. What else?
I have a question.
Yes.
Asking, would you guys be able to put your AOS on GitHub so other people can contribute to it?
You're jumping ahead. We have a slide on that.
All right.
I will get back to that. We are trying to figure out what that looks like. If you are interested, please reach out to us and help us figure out what that looks like. But it is a place we're trying to take this. Okay. So what else can we do that's fun? So event loop inception. So we said before, context switches are expensive. What we also want to be able to do is have people write smaller, simpler modules. So instead of maybe writing an entire superstructure, we could have a little module that's for the flywheel and a little module that's for the intake, for example, and then we could just plug them together and a little module that makes them work together. And that would be kind of more flexible and let us reuse code better. So that would be cool to be able to support. So what could we do? Well, if those are two event loops, we could actually just have a way that we schedule those on the same thread. Because that way, when our one part executes, it would just trigger the next part in the same thread. We wouldn't eat the context switch, so it'd be pretty cheap, and just schedule them together. And then we could have that interface with event loops outside as well. So what this would let us do is decouple kind of how we're scheduling and how we're running our system from how our software developers are designing it. So we get more flexibility there and can change decisions easier. So this is pretty cool. So we introduced a new concept, potentially, where we have event loops scheduled together on a thread, but we didn't actually change any of the interface with our user code. So that's pretty cool. Okay, so let's look at another example. So say we want to simulate something. So we have our 2020 robot. We went and recorded a match, say in our practice field or maybe at a competition. So we can take this log file, take the images from those, pass them to our cameras, run our processing code. We can publish all the drivetrain, our gyros and encoders, and then we can go have our drivetrain estimate where it was and what was happening. And same for superstructure. We can see how that would have reacted. So this lets us take data, potentially even match data that's very expensive to accumulate and very hard to try new things with and very slow to interact with. And this lets us interact with it and try stuff. This is pretty cool. Okay, so let's summarize. So what are some of the cool things that we introduced and what do they enable us to do? So callbacks in the event loop, that abstraction, let us hide the scheduler and support simulation and robots. So that's pretty cool. So we were able to introduce a pretty lightweight abstraction and get some real benefit out of it. So another thing that we end up doing here is we provide consistent guarantees between implementations. So we talked about wanting to run the same code in simulation and on the robot. Well, to do that, we need to have the same interface between the two. And this really starts to push us towards really ensuring those two behave identically. So we take that very seriously. Last time I checked, it's about 2,000 lines of test cases. And these all go and, schedule a timer, send a message, and make sure it all happens in the right order between all implementations of the event loop. So we're really big on making sure that the behavior between all these implementations is very consistent. So that means that if you find a bug in simulation, the odds are it's also a bug on your robot. And the same is also true. If you find a bug on your robot, you can take a log home and reprocess it and very, very likely refine that bug in simulation where you can fix it. The other assumption we're making, which is not necessarily explicit, is callbacks take zero time. So this is really, if you have your control loop and it's executing every 5 milliseconds, we're assuming it finishes before the next control loop cycle, because that callback needs to finish before you can process the next message. So for most robots, this works. There are some cases where you have like some plant, you're trying to do a path planner or something, and it takes a lot of time to compute, where you have to start to break these assumptions. So this is just something to watch for. We have not actually found it to be a constraint on what we're doing. We saw a reflection API and we saw some of the cool things we can do with that. So reflection really lets you decouple some of the generic tooling from your specific robot and reuse it across years. So far, we've succeeded in making everything interesting a message. And we have a bunch of tools, including Logger, to manipulate those messages. So like we can put a message on a web page, we can go look at it on the command line, we can replay it, we can all these things. I say all here in asterisks because there are some cases where like you can overwhelm your system with data as you start to build larger and larger systems, and you can't actually afford to log everything. So there are some cases where we want to pare that down. But where possible, we don't really want to be making compromises here. And then another strong preference is we're choosing to statically configure things. So everything is logged. We can log that configuration because it's very fixed. We can enforce it. But it does mean that like we can't have a bunch of robots in a swarm that come together and we change counts and things. We do not support that. We pushed on this a little bit, but we try and make it hard to use AOS incorrectly. And also we try and tell people very quickly. So on multi-node, where we talked about trying to make it so you couldn't accidentally subscribe to something that wouldn't get delivered, we want to do that everywhere. Any place where we can find a pattern that doesn't do what we expect or is against the usage of AOS, we want to try and detect that at startup, and we want to try and reject that. And this has let us build some pretty flexible things. So, and then kind of the last point, kind of how does this apply to various robots? How do these concepts apply? And what are you looking for? By having these set of tools that we've built that are extensible, we're able to build more complicated algorithms more efficiently. So this is the type of stuff that you want to do as you start to build autonomous vehicles. So, hey, let me go record a data set of driving around town, and then let me come bring it home and save a bunch of these, rerun all my algorithms as I keep developing them, and see how we would have responded, and build up this library of interesting events and make sure we can do the right thing. That's more of a simulation or a replay. Testing is very similar. Like, how do I stimulate my system in certain ways and see how it responds? And then automate, checking the response to that. So that's pretty cool. Okay, so then we'll get kind of to the question Mira just asked. So we have a bunch of documentation. We've been releasing things on our website. We have some design docs. Some are a bit ahead, some are a bit behind. And we are working on moving AOS development more into the public. We've added contributors to our private repository in the past. That's not a great answer. We are trying to figure out how to get it on GitHub or something similar so we can really grow the community. We've definitely had some outside contributors over the years, especially in the last year. But yeah, this is something we're really interested in. We're really trying to figure out how to push that and help make this thing become bigger. So I'm certain we'll be sharing the docs, the slides later. So there's a link to the docs, link to docs on the queue implementation, timer report, logger. We're trying to leave a bunch of documentation behind to help explain what's going on. Cool. So that's what I have. Did you have any more questions, Mira?
We have another question.
Perfect.
Do you guys have your own custom low-level C libraries, or do you use standard ones?
A little hard to interpret that. We use a lot of the standard C libraries, or C++ normally. So our lockless queue is all built with a standard C++ library. For real time, you want to avoid allocating memory dynamically. If you start to read up on allocators, you'll see how sometimes they have to ask the AOS for more memory. Sometimes it's not available. You have to search around for an open block that you can use and all sorts of crazy stuff. And you just really don't want to be doing that in a real-time environment. So we've built up some various little libraries to automate some of those things and make those easier. Then we use those. But by and large, we try and use the standard library where possible.
I have another question. Can you start a simulation with a log file, then cut it off and let it go on its own?
Yeah, nothing saying you can't. You would just deregister you would just kill the log reader at a certain point in time and let everything keep going. I've not done that one personally, but there's nothing in the code that would prevent you from doing that. That's a fun idea. We may have to try that sometime. One of the cool things we have built are this concept called interceptors. The idea is, let me find a picture. We'll pick on ping and pong because they're easy. Okay, so we have ping sending messages to pong and pong sending them back. Well, what if we want to test what happens if every other message is dropped? So we can put a little process right in the middle here, a little module, and have ping send to it, and then it send to pong, and then that lets us go and modify the messages. So we could corrupt them, we could drop them, we could do all sorts of crazy little things there, and then see how our system responds. So I've built some really fun tests where you have kind of a nice, beautiful log file, and then you just kill an encoder and just drop all the data from it and see how your system responds. Or other little tests like that. And it's really interesting to see and kind of test it and learn.
That's all we have. So thank you so much,
Cool.
Austin.
Thank you for everyone for coming and for your questions.
And thank you to everyone who came to any part of the Spartan series. We hope you had fun and learned something new.